Okay, excellent. Yes, thank you. I am starting off by explaining the just a bit of the mission summary and the performance of the sampler, where we are owing to the Itokawa samples. But this background, this is a series of asteroid sample return, past, present, and even future, including now the Chinese at the bottom on the right. Next, please. So here's the agenda. I give you a little bit about a mission summary of the Hayabusa mission, Hayabusa 1 mission, and then what we have learned about Itokawa in this mission. And then I focus on three aspects of the impact sampler of the Hayabusa design capability and operation consequences and eventual verification by Hayabusa 2 mission. Next, please. Okay, next, please. Okay, here's a little summary. So the Hayabusa was almost 20 years ago. Can't believe it. Launch. It's not defined as an asteroid sample return mission, but rather it's a technology demonstration mission for asteroid sample return. So that means that by verifying all the technology we required, including like ion engines or autonomous navigations, microgravity sampling, and the direct capsule re-entry to the Earth atmosphere. Only if we succeed all those technology in a series, then at the end we will receive sample from asteroid surface. So it's a very challenging mission, but so therefore we defined the very first one as a tech demo, and without this tech demo, we didn't have Hayabusa 2 or maybe MMX. So it was launched in 2003, and they made one gravity assist in 2004, and then made it rendezvous with Itokawa at the target in September of 2005. And originally, we planned to stay only 3 months at the asteroid. So therefore, just 2 months after the arrival to the asteroids, we conducted the very first surface sampling, and then a week later we performed the second one, because we wanted to leave the Itokawa by December 2005, but there are an array of the malfunctions occurred, especially for the thrusting system, and we lost temporarily the communications, so that we decided to stay one more orbital period of Itokawa. I mean, two orbital period of Itokawa, which is about 3 years extended mission. So therefore, instead of returning to Earth 2007, but we departed asteroid 2007 and then returned to Earth in 2010. Next, please. Okay, here's orbital trajectory. Basically, it employs ion engines, which means that we intentionally divert from Keplerian orbit, and then we had gravity assist by the Earth, and then change the course to similar orbit as Itokawa, and then arrival of the Itokawa, and then. On the return trajectory, left asteroids in 2007 February, and then make one revolution, and then 2010 June Earth return. I would like to note that because of this, the Itokawa is actually the farthest object the ISAS or Japan has ever arrived and still operated. So the Itokawa is our record so far, and second farthest object is actually Ryugu, and the third farthest object is actually the Mars. Next, please. Okay, so and then we had Earth return capsule landed on the Umela Desert in Australia, June 2010, and then conducted by subsequent initial sample analysis, and I understand that some of those people on these pictures are now attending the conference. Next, please. So that's a quick summary of the mission, and then the next, what I would like to explain about what we learned about Itokawa through this mission. Next, please. Okay, so we did carry scientific instruments, and then data acquired is still available today on the full on the web page of the ISIS. The right hand side, it's a cartoon that's where the co-alignment of the field of view of each instrument. Amica is optical camera, and the laser altimeter lidar, and the near infrared spectrometer NIRS, and X-ray fluorescence spectrometer or XRS in these fashions. The camera, we had more than 1,600 images, lidar 1.7 million points, NIRS 120,000 spectral data, and XRS produced 50,000 spectral data in 2 months. And then on top of these, we also had the opportunity to have a free trajectory measurement by a range and range rate through telecommunication between Earth and the spacecraft. Then we were able to have a gravity mass, therefore bulk density. And then by knowing a three-dimensional volume by Amica spectral image, stereoscopic images, then we should be able to get the macro porosity, assuming the S-type asteroid Itokawa, the bulk density is consistent of L chondrite, ordinary chondrites. We also carried a tech demo for the first asteroid rover, Minerva, but we didn't get the rover landed on the surface. And the sampler, we collect the surface sample somehow, but it was less than 100 milligram. Next, please. Okay, so microgravity geology has initiated. So that we had Itokawa has two distinctive or dichotomy between rough terrain and smooth terrain, and then by having a free trajectory arc, we had the measurements of the average density, and then later we actually calculated macroporosity, which is about 40%, and so that as you can see, Itokawa is by far the smallest asteroidal body we ever encountered and measured. And we also discovered a granular migration movement by low geological potential. That's where we actually collected samples of the so-called smooth terrain at the bottom of geopotential. Next, please. Okay, so this is a summary of the fundamental parameter of Itokawa, reviewed by Itokawa, Hayabusa. In the yellow color, the letter in the yellow color is actually the data we have obtained and calculated as a result of this mission. Of course, we used to have much crude size, like when we had ground light curve model of Kasalainen et al. And the Itokawa looked like that on top left. And then we had a ground radar model by the Steve Oster et al. Was in the middle. But once we arrived to the asteroid, that's the bottom left is what we got by Amica images, 8 color filtered images. And then we had finer size determination. And the spin axis, not only for orientation in space, but also on asteroid itself. And then the mass was able to calculate the 4 digits, and then bulk density. It was defined. It was quite a bit of debate, but in the end, we settled down something around 1.6 plus minus 0.1 gram per cc. Next, please. And then, as Tomoki-san said, one of the greatest challenge, the advantage of having in situ measurement and bring samples back from the asteroid we have measurement by spacecraft is that the connection of the asteroid taxonomy with meteorite types.
We have
This
10
is
minutes left.
okay. Thank you. Yeah, this is a summary of the news. The link between S-type asteroids and ordinary chondrite meteorites. That's obvious here. Next, please. And then once the sample returned, there's a number of the initial science paper, special issue of science paper about Itokawa sample analysis. First, excuse me, have to prove that it's extraterrestrial, and then the Nobis science work actually revealed that the so-called asteroid meteorite paradox was actually due to nanophase iron or space weathering effect in top surface of stone S-type asteroids. And then Tomoki-san's work is actually gave us approximate aging of the parent body. Next, please. So at the end of the special lectures, a special series that we had sort of the scenario of the past, present, and future of first visited rubble pile asteroid Itokawa, like this. Probably everyone knows this. Next, please. Okay, so then the rest of the talk will about sampling devices. Next, please. Originally, since this is the very first asteroid sample return, there are a number of great ideas, and we made a design trade-off of the whole lot, starting from docking robots and drilling cores and robot arms and rotating brushes and gas injections and then bullet projection. Some of them, gas injection was actually used by Osiris Rex, and robot arm and drilling coring will be used in MMX. But at that time, in late 1990s, no one knew there are such a huge legless surface, even such microgravity body. So that the bullet projection was selected because if the bullet is impacted on the monolithic and then we fracture the surface, or if it's in the regolith, it's uplifted, and because of the microgravity, so we actually collect those fragments or uplifted regoliths, the either cases, so that bullet projection actually didn't get restricted by the surface condition of the target. Next, please. Okay, so yeah, I said that. So we had a tantalum projectile to making sure we are not confused with artificial material contributed to the natural particles. And at the launch, it was extracted and extended for about 1 meter long fabric home. And then once projectile fires, then multiple bounces occurs in interior of the home, and then eventually introduced into the smaller volume of container, or we call it catcher. Next, please. Okay, and this is the results of our ground test, including 1G and the microgravity for the drop towers, and then both monolithic and powdery regolith. And for either case, we are able to find in microgravity conditions 100 milligram to 10 gram at the best. So that was a condition we initially thought. Next, please. Okay, and then after that, we have to insert the collected samples in the catcher into the capsule. So, and then latch it, and then so the latch was actually confirmed. Sorry, in Japanese, with a temperature sensor at the attached to the capsule, and then thermal inertia will change because of the physical contact of the metallic portion. So that was confirmed. And then when sample catcher returned to the Earth, and then we initially conducted X-rays computer tomography, We before opening the container, but we are expecting if there are huge amount of the samples, we should have been able to see those through XCD before opening it, but we didn't see any. In other words, at that point, we said at the best, the size of the particles must be around the resolution of this X-ray CD. Next, please. Okay, and then what happened on the asteroids? Next, please. So we need to find first. We have to have site selections for both scientific reasoning and also engineering feasibilities, and then approve. We discuss with the joint science team and approved by the consensus building, and then we put into the operation sequences. Next, please. So we decided to have a smooth terrain for the both sampling, first touchdown 1 and 2. We just at that time we call this Medici Regio. That's it, the only equatorial region where it has smooth terrain without worrying about as the spacecraft getting hit by the border equivalent size of the spacecraft. Next, please. So and then we during the descent, there are a number of sensors we have to employ depending upon altitude. So we call it the gate position, home position, science tour, site selection, and the touchdown. So a number of different things. Next, please. And then quick to the touchdown. For first results that during the descent, the obstacle or this was detected by the spacecraft, a fan beam sensor. It may be some levitation dust. It's still inconclusive. But so therefore, the sampling sequence was automatically aborted as originally designed. So it was not a mishap, but it was the spacecraft properly aborted. However, what we didn't expect to happen was that actually spacecraft kept descending and then the bounce on the surface twice, and then therefore drifted from the original touchdown target point, drifted to the high altitude region, and then stayed there about half an hour while keep thrusting the LCS. Next, please. For the second touchdown, it was finally performed the perfect touch and go sequences, only duration of 1 second. However, the safeguard program was actually inserted just before the firing the projectile, so therefore the projectile fire was aborted once again. But the touchdown was conducted and then safe ascent in 2 seconds after that. Next, please. And for both cases, the capsules actually catchers closed once it's in the space. So this is results. So 2 landing sites reworked by the trajectory results, and then touchdown 1 is actually far higher altitude than the target marker, and the touchdown 2 is pretty close. So the touchdown 1 is where the room B, samples from, and the touchdown 2 is where the room A samples are from, and then actually touchdown 2 region is just at the edge of so-called Shirakami Cliff. It's a very steep slope where those the rounded eroded samples are collected. And the maximum size of the samples apparently it's a room A was 320 microns, and both sites has a size distribution peaks in 30 to 60 microns. Next, please. Okay, and then so that everything it worked for the sampler except firing the projectile. So then we had second chance, but we waited another 10 years for the verification. Next, please. That is Hayabusa 2. So the Hayabusa 2 sampler is exactly the same design as Hayabusa 1. Next, please. And then we performed the two touchdowns, the surface touchdown and subsurface sampling. And then, as you can see, this is actually the sort of accumulations of that. The blue area is where the Hayabusa sampler design required from 0.1 to 10 gram, depending upon the monolithic to powdery. And then we also had.
It's already 20 minutes, so wrap up and finish your talk, please.
Okay. Yeah. So thank you. Yes. So this is the last page, and but in for the for the Yugu we have. Okay. Next, please. Thank you very much.